Hi, in this paper we present a framework for the design of wireless networks in industrial environments, enabling factories of the future and Industry 4.0. Factories, industrial warehouses and processing facilities are typically characterized by large room dimensions and the presence of blocking objects, such as metallic racks and machinery. In order to provide wireless connectivity in the complete room, more than one access point is required. Now, one of the challenges is to define the locations where access points should be placed. A second challenge is that in real-life deployments, there is no single wireless technology that can or should be used. Some technologies are suited for wireless sensor networks with low data rates, such as Zigbee, LoRa, Thread, Dash7, and Z-Wave. But we might also need wireless local area networks, such as Wi-Fi, that are suited for high-throughput links used for video monitoring in an industrial environment. There are also new technologies, including software-defined networking, that will be used in factories of the future. Therefore, we propose to use a hybrid network in which multiple technologies coexist with multiple levels of reconfiguration options. Another challenge for industrial environments is that the floor plan regularly changes. For instance, when the assembly line of a car manufacturer changes or when machinery is added in a processing facility. To cope with floor plan changes, we propose to use monitoring data to automatically reconfigure the access points in order to guarantee quality of service. In our framework, we have three phases. After the initial network planning, where the location and configuration of access points is defined and a coverage map is calculated based on a statistical path loss model, we acquire monitoring data from the clients. And in the second phase, we perform a calibration of the calculated coverage map based on actual measured data. We then enter a monitoring loop in the third phase, where the monitored data is compared to the required quality of service. When the quality of service requirements aren't met, for instance, the RSSI drops due to added machinery that blocks the RF path, a reconfiguration of the access points is triggered. To have headroom for the reconfiguration, we don't use the best possible settings during the initial network planning. For instance, by not using a maximum transmit power, more access points are needed to provide full coverage, but when machinery is added after the network rollout, we can still provide quality of service by increasing the transmit power. I invite you to read our paper published in MDPI Applied Sciences for the detailed presentation of the reconfiguration algorithm and validation via simulations. We also implemented the algorithm to test the reconfiguration in a real-life scenario, in a lab measuring 30 by 11 meters. The tool determines the location of access points based on the floor plan. The access points are visualized by circles and the clients are represented by hexagons. Data streams are set up between the different clients and monitoring data is gathered via in-band network telemetry. In this demonstration, you see that a calibration is performed for all clients, and then we continuously verify RSSI monitoring data and check that the requirements are met. In this case, a throughput of 54 megabit per second for Wi-Fi and a throughput of 250 kilobit per second for Zigbee. As you can see, we also monitor jitter and end-to-end latency of the link next to RSSI. A green line between the clients indicates that the quality of service requirements are met. In this example, a data stream is set up between two Zigbee clients via a single Zigbee coordinator. We artificially decrease the received power at the RF input port of one of the clients and see that a reconfiguration is triggered when the closed-loop monitoring system is active. In this case, the software-defined radio that is Zigbee compliant switches to a narrow bandwidth channel to decrease the receiver sensitivity. And after the reconfiguration, we can further increase the attenuation and the data stream between the two clients continues. When the algorithm is not running, the communication stops when the received signal strength reaches the receiver sensitivity. Thank you for your interest in our research and feel free to contact us if you have questions.